So we're not doing a problem of the day today because I want to really briefly go over arithmetic sequences. We're not going to spend too much time on them, but I want to cover them, and so we're just going to talk about them briefly. Note, we are skipping the section 10.2 and going right into 10.3 for your homework, okay? So 10.2 is arithmetic sequences, which we're going to talk about briefly, but we're not really going to work on. So your homework is in 10.3. That's on page 761, numbers 1 through 25 odd. So, okay. An arithmetic sequence is a sequence defined by a common difference. So let's just get a general looking sequence out. There's A1, here's A2, then comes A3, I think the next would be A4, and so on, all the way up to a N. We'll just talk about the first N terms of the sequence. And if it's an arithmetic sequence, what that means is that each one of these pairs has a common difference. So if you take the next one and you minus off the previous one, so A4 minus A3, or A3 minus A2, or A2 minus A1, you get a common difference. So for instance, if we had the sequence 3, 7, 11, 15, and so on. Now, again, I said last time, or a few times, or was it last time, that you can't tell just by looking at a sequence whether or not what the next term is or something like that. But if you know that it is indeed an arithmetic sequence, then it has this property. So what we could do is we just say, okay, we look at these two pairwise, right? We take any pair, next ones to each other. We say 7 minus 3 is 4, right? And now we have this pair here. 11 minus 7 is, hey, what do you know? It's 4. 15 minus 11 is, what do you know? It's 4, right? And that's the case for an arithmetic sequence. That's what makes an arithmetic sequence. So the difference between these two, A2 minus A1, is D. The difference between A3 and A2 is some constant difference, D. Okay? Now, let's think just in terms of this sequence right here. Another way we could wrap our heads around this is saying, well, if the difference is the same, really, how do you get from 3 to 7? You're starting here at 3 and you go to the number 7. Well, you added 4. It's a distance of 4, right? So we could say that this sequence is 3, and then you just take 3 plus 4. Then the next time, to get to the next one, yes, you just add 4 to the previous one. Or we could say, to get to 11, if you start there and you go 2 of that same distance, so 4 and 4, you could get there by going 3 plus 2 times 4. That's how you get there. 3 plus 2 times 4 is 3 plus 8, which is 11. Right? Then to get to the next one, you add on, yes, another 4 in distance. But then now the total from there to there would be 1, 2, 3 of the distances, right? 3 4s. So you go 3 plus 3 times 4, and so on, right? And let me just check. 3 times 4 is 12, plus 3 is 15. Yeah, okay. We're at the right place, right? And that is like kind of the defining feature here, right? Well, I mean, that is there's a common difference, but we could write this in a different way. And so, in general, what we could say is, if this sequence is arithmetic, then by definition it has a common difference. And so we could rewrite this as A1, and then how do we get to the next one? And again, I like this visual, right? You know, we're starting here at some number, A1, on the real number line. And then you add a distance D to it to get to the next one. That's A2, but that's the same thing as A1 plus D. So you have your A1 plus whatever that distance is. Distance or difference, it's nice, you know, I use D in both cases. Now you go one more of the same distance, D. You've gone a total of 2D from the beginning, and you get to the next bit, which is A1 plus 2D. And so on and so forth. So A3 would be A1 plus 2D. The next one would be A1 plus one more of them would be 3D. Now here's the question. AN, what's the formula for AN? Pause it and figure it out. So, if A2 was A1 plus 1D, if A3 was A1 plus 2D, A4 has the 3, right? You're always one behind whatever that is. 2 is 1 less than 3. 1 is 1 less than 2, and so forth. So we would expect that AN would be A1 plus, not N, but N minus 1, whatever the previous one is. And yes, this formula here, so what I've just derived here is the formula for the nth term is whatever the first term was, plus N minus 1 D, right there, okay? And yeah, we could check that, right? It should be, just using this formula, it says that A4 should be A1 plus 4 minus 1D, which is A1 plus 3D. And that's what we found by doing it, you know, visually and all that. So, yeah, that's about it. There's not much more to say about that, except one thing. What did we start doing with sequences last time? We started adding them up. We found the sums. Well, what we were particularly interested in were the partial sums of a sequence. And so just to remind you, the partial sum, we denote it like that. The nth partial sum of a sequence, A, is what you get when you add up the first n of these guys. So there's your A, K, right there, right? And so what is that? Well, that's A1 plus A2 plus all the way up to AN. Okay? Now, an interesting thing happens if you know that this sequence is arithmetic. So just to be clear, what we're doing here is this. We're trying to compute what this is all the way up to the nth one. Now we have a nifty little formula for this guy, as we just had on the board, right? What is A1? Well, A1's the first one. There's nothing there. But what is A2? A2 is what you got when you went A1 plus D. You add that to what's A3? Well, that's what you got when you did A1 plus 2D. And I don't have them here, but we'll do the next one. A1 plus, how about 3D? And so on, all the way up to the last one, which is A1 plus N minus 1 D. Okay? So that's the partial sum. That's what you would have if you did all that. But we could rearrange this, and maybe it'll come out to be nice and something easy to compute. Right? This is just taking a bunch of numbers and adding them together. We could do that in any order. So why don't I group all the A1s together? And then I will group all the other stuff together. And so the A1s are all over here now. And now we have a D, 2D, 3D. So we have a D plus 2D plus 3D all the way up to the last one, which in this case is not ND, it's N minus 1D. Okay. Like that. Okay. Now, of course, we're talking about the nth partial sum. So how many terms are in my sum? Well, n, right? Like by definition, there's exactly n of these things, which means there's exactly n a plus 1s, right? And so a plus 1 plus a plus 1 plus a, a1 plus a1 plus, how you do that n times, that's the same thing as just taking n times a1, right there. Now the cool thing about this is what's left in the rest of this thing, there is exactly 1D in every one of these terms. So I could factor out that 1D. And as a matter of fact, I think I'm going to factor it out on this side, right there. And what's left? Well, if I pull out the D from here, I'm left with a 1. Pull it out from here, I have a 2. Pull it out from here, I have a 3. All the way up to N minus 1. Okay, so let's just check that, okay? n a1s. Yes, that's the same thing as a1 plus a1 plus a1, a total of n times. This, if I factor him back in, I'll have my n minus 1d all the way down to 3d, 2d, and just d by itself. And that makes sense. Now this might at first be like, wait, you're missing one. There's only n. I'm sorry. There are n terms here, but there's only n minus 1 terms here. Yeah, but remember that this first term didn't come with a d, did it? Right? It was the second term that brought in the d, then the third term brought in a d, and so on and so forth. And so we do expect that there are n minus 1 d's here in this expression. Now, recall from last time, we have a nifty formula for this thing, right? So we derived last time that the partial sum of n things, and we'll do it this way, 1 plus 2, the partial sum of the first n, we'll say capital N natural numbers. We had a cool formula that was n times n plus 1 over 2. And so now we're not going up to capital N, we're going up to n minus 1. So if I just replace this with an n minus 1, let's see what happens. We have our n minus 1 right there. I'll replace this with the n minus 1, n minus 1. And then I'll replace this one with an n minus 1. This is going to look terrible. I should have given myself some more room. Sorry. N minus 1 plus 1. So we have n minus 1 times n minus 1 plus 1 is just n, just plain old n, all over 2. Okay? So I could rewrite this entire bit right there with this nifty thing. So that's what I'm going to do. Let's get this stuff out of the way here. I'm going to say this is the same thing as n a1 plus I have n minus 1 times n over 2 times d. Let's check that. That whole thing is that right there, which is that. Yes. Okay, that looks good. But we can simplify this a little bit more. Now, first off, this is a perfectly good formula if you wanted to know the nth partial sum of any arithmetic sequence. As long as you know what d is, as long as you know what that common difference is, and you know what the first term is, you just plug it into that formula and you're good to go. But maybe we could simplify this a little bit. Maybe we can, maybe we can't. So what I'm going to do, to give myself some room, I'm going to write this right up here. Okay, I'm going to say this is the same thing as n a1 plus n minus 1 times n over 2 times d, just like that. Now let's give myself some room. And again, perfectly good formula. I'm not a big fan of memorizing formulas, and maybe you could tell it since we're not even going to go, like, we're not having any homework in this section. It may not be that important, but this is kind of interesting, something that's about to happen, and I think this is pretty cool. We're going to talk about it briefly, but notice I have an n in both terms, okay? So I'm going to factor out an n and see what's left over, a1 plus n minus 1 over 2d, like that. Now, one thing that's you might notice is that this looks very familiar. It's very close to that. The problem is we have this over 2 bit. So maybe I could factor out that 1/2, right? So like if I have x plus y over 2 and I want to factor out the half, I bring the half out. That guy is fine like that, but now I need to have a 2 up in the numerator, right? And let's just check that, right? Factor him back in, and the 2 kills the 2. The half comes down into here, and that is what exactly we should have. So I can factor out the half by bringing him out here like that. Now let's just double check. What's left over here should be my n minus 1 times d. Now I needed 2 in the numerator here for my a1. And does that make sense? Let's just double check. Bringing the 1 over 2 back in kills that 2. Bringing him in here puts them in the denominator. So yes, this is the same thing as that. We're good to go. We're almost there, but I have a 2 there. Well, if I rewrite it like this, I say n over 2. How about 2a1 is the same thing as a1 plus a1, right? Last time I checked. Yeah. a1 plus a1 is 2a1. Okay, cool. But now, check this out. This right here, that is the nth term. That's the definition of what the nth term is. So this is the same thing as n over 2 times a1, there's your a1, and all of that right there, that's your an plus an. And you're like, oh, that's much simpler. It's even cooler than that, right? It's not just simpler. Check this out. This is really cool, because if I bring that 2 in here, a1 plus an all over 2. That is just the average of the first term and the nth term. It's kind of interesting. This says if you take the average, so given an arithmetic sequence, that's a sequence that either increases or decreases, right? We didn't do that. The one that we did at first was, we had a 3 and then it went up by 4 each time, right? It could have gone down. You could have started with 30 and then you go, let's say 28, 26, and so on. That's an arithmetic sequence. It's decreasing, but there's a common difference. That difference happens to be a negative number. No big deal. It's just a negative number, right? It's negative 2 every time. The difference is negative 2. Difference is negative 2. And so each time you do this type of thing, and it'll take off 2 more, and so on. So that's fine. But the point I'm making is you have any arithmetic sequence, and you want to add up all the terms. Apparently, or you want to add up n terms. Apparently all you need to do is take the average of the first term and the last term, and then just multiply that by n. Let's see what's going on, because that seems a bit, I don't know. I couldn't have predicted that. If you said, if you had proposed to me, hey, I want to add up in terms of an arithmetic sequence, then all you have to do is take the average of the first and last term and then multiply it by the number of terms you have. I would say, no, you're going to have to prove that to me. Well, we've just proved it, but it doesn't seem intuitive. But now let's just kind of think about what's going on here. If we think about this arithmetic sequence as a function, which we did define all sequences as functions, right? Let's just think about what's going on here. So, an interesting thing about the sequence being arithmetic. So here's 1, here's 2, here's 3, here's 4, and let's just say we're going to do 5 terms. We want the 5th partial sum. Since it's arithmetic, it has a nifty little property here. So like the one we used earlier, every single step over you go up by the same amount, right? Like we had 3 and then we went to 7. The difference was 4 between these two, right? We go over 1 more, we go up another 4. We go over 1 more, we go up another 4. We go over more. In fact, all of these lie on a line. So, in a sense, an arithmetic sequence, you can think about it as it's like the sequence form of a line, right? That is what a line is, right? It goes up to 11, then to 15. Oh, I drew this all weird. Sorry. 15 and so on. And then what would the 5th one be? Because there's 1, 2, 3, 4, 15. Another 5. That would bring us up to 19, right there. Okay. So what this says is take the average of that number and that number. So 19 plus 3 over 2. 19 plus 3, 19, 20, 21, 22 over 2. 22 over 2 is 11. And 11, hey, what do you know? It happens to be that one right there. Because I chose an odd number of it. It works out that, yeah, it is one of those points. But anyway, the idea here is we're trying to compute. You could think about it like this. We want to add up this number, like this much stuff, plus this much stuff, plus this much stuff, plus this much stuff. And we want, like, you could think about it as area if you like. You can say, what's the total area that we're adding up here? And we could either do that this way, where we add up each one of these boxes. You add up 3 plus 7 plus 11 plus 15 plus 19, which is whatever it is. I didn't bother to do that. Another way of doing that, given that this is a line, another thing you could do, it says, take the average. Well, what's the average? Well, it's this middle bit right here, right? The average, you could think about it as being halfway between these numbers, which happens to be 11. Now, if it were an even number of things, it might not have come out that way, but, you know, in fact, it wouldn't, because halfway between would be somewhere in the middle of an even number of numbers, at any rate. So what this says to do is you find the halfway point, and now you just add that many of those things together, n of them. You find the halfway point, you find the average, and then you add up that many things. So another way of getting the same bit would be to say, okay, find the halfway point, and now for every one of these boxes you have, add up this much. And so you're overestimating down here where it's less, but you're underestimating by that same amount right here, right? And so for each one of these, all n of them, there's 5 of them in this case, right? It says that, basically what this says is that the blue area, which is that plus that plus that plus that plus that, is the same thing as the red area. That plus that plus that plus that plus that. I think that's kind of cool. You'll see something very, very, very similar to this in calculus. But yeah, so again, it doesn't really come up. And when we do it in calculus, it won't be like in terms of sequences and stuff like that. I've rarely ever used this stuff. But it's I do want to present it because if you do see it in the future, now you've seen it before, and now you have a place to go to refresh your brain on this stuff. But as of right now, we will not be coming back to arithmetic sequences unless I might give you a question like, is this sequence arithmetic, geometric, or neither? I might give you something like that. Geometric sequences are sequences defined in the following way: that the ratio between the next one and the previous one is constant. And we're going to use R to remind us ratio, the same way we use D to think about either difference or distance. I like to think about it as distance. But here we're using R for ratio. Now I'm gonna go ahead and apologize in advance, because in a little bit I'm gonna change it from R to something else, and I think it's worth it. But for right now, we're gonna use R. And so to be clear, what we're saying is you take the next. If I take A2 and divide it by A1, A2 divide by A1, I get a constant R. It's the exact same thing if I take A3 and divide by A2. I get the exact same R. If I take A4 and divide by A3, I get the same R. Okay, so here's an example of one. 3, 6, 12, 24, and now. Okay, so see if you could tell what R is. What you're going to do is just take the next one, divide by the previous one. And if we take 6 divided by 3, we get a 2. Is it the same thing if I do 12 divided by 6? Yeah, I still get a 2. Is it the same thing if I take 24 and divide by 12? Yep, I still get a 2. So it's a constant ratio between each pair as we go along, okay? And again, like the last time, I'm showing an increasing sequence, but it could go the other way, right? I could have it decreasing. Like for instance, if I had this sequence 8, 4, 2, 1. Now I go 4 divided by 8 is a half. So that would be my R. Because 2 divided by 4 is a half. And 1 divided by 2 is a half. And so on and so on and so forth. So, in general now, this lets us get a formula for n. Because in the same way, right, we start with A1. And if A2 divided by A1 is a constant ratio, well then I can multiply both sides here, bring my A1 up, and I get my R. So A2 is A1R, right? And then each time, and you kind of saw that before with the sequence I just had here. In fact, the way that I did it, I just chose a number, 3, and then I chose another number, 2, and I took my original number and just kept multiplying it by 2, right? 3 times 2 is 6, times 2 is 12, times 2 is 24. And that's exactly how I obtained this sequence when I wrote it down right here, right? And so here we had 3, and again this was 3 times 2. This was 3 times 2 times 2, or how about 2 squared? This is 3 times 2 times 2 times another 2, or how about 2 to the third, and so on and so forth. And this is the same thing here. If it's a geometric sequence, is the type of sequence that does exactly this. That each time you're just, to get the next one, you multiply by this common ratio. So this one is A1R squared. This one is A1R to the third. And now I'm going to ask you to pause it and figure out a formula for AN, the nth term. Kind of like the same thing before, right? It's the only thing that's changing is the power. We know it's going to be A1 times R. It's just how many R's have we multiplied at this point. And just like before, right, when it was 2, we had to the power 1. Or we even could write it as A1R to the 0 right there. That might be useful in the future. But right now we're just going to think about it like this. We say, okay, so when the index is 2, R is 1. Or the power is 1, right? When it's 2, we have a 1. When it's 3, we have a 2. When it's 4, we have a 3. So when it's n, we should have an n minus 1. And so that gives us a formula for the nth term. If you know the first term and you know R, you just go R to the n minus 1 to find the nth term. So, let's do a couple examples here. So I'm going to get rid of this stuff here. So, but before we do, I just want to say, I don't really think about it this way. A geometric sequence I think of in this way, that it's a thing that you get when you just multiply by some constant number each time, right? You take, to get from here to here, you multiply by R. To get from here to here, you take the previous thing and then multiply by R again. To get the next one there, you take the previous thing, multiply by another R, and it brings you up. That's what a geometric sequence is, okay? So we define it by saying there's a constant ratio between, but what does that really mean? To get the next one, you multiply by some number, and it's the same number every single time. Okay, so number 2 from this section right here, it says, given that we have a geometric sequence, given that what we have here is a geometric sequence, find the common ratio. Now, just I said that like 3 times. Given that it's a geometric sequence, why did I make such a big deal about that? Well, because if, you know, I gave you this to begin with, 3, 6, how did we do this? 12, 4, you might look at that and go, oh, yeah, that's a geometric sequence. But remember the example I did the other day, right? This is not enough because we could go anywhere with this. Because sequences can be like completely random. They don't need to follow patterns. Like any sequence, like if you take the digits of pi, that's a sequence. We could take the, 3, 1, 4, 1, 5, 9, 2, and so on and so forth. It doesn't need to be a nice pattern, or you might have a nice pattern, and then in this particular sequence, then it does 105, then it does negative 337, or something like that, right? We don't know right off the bat whether or not it is. So you have to be told that, yes, indeed, what we're about to write down is geometric. And you look at that and you go, well, that's got to be a geometric sequence. Yes, probably. But here we go. Okay, so that's not the one. From number 2, it's this. It says, given that this sequence is geometric, and it gives you 1/7. And it gives you 3/7. Then it gives you 9/7. And so on. They give you an nth term, which makes this a really easy problem. We're not going to do that. We're going to say, okay, given that this is a geometric sequence, find the common ratio. Well, we find the common ratio by taking the next one, divide by the previous one. So that ratio, if indeed it is geometric, it will be the same no matter which ones we choose. So I'm going to go ahead and do this. Take 1 and then divide by the previous one. That's what that is. And so now that's the same thing as doing this, right? To divide by a fraction, you multiply by the reciprocal. That comes out to just a plain old 3. Now, I'm done, technically, because it told me it was a geometric sequence, but it's nice to just check. I recommend that as you're learning this stuff, you just check. So I'm going to check and see, is it the same if I take this one and divide by that one? Is this the same? Do I get the same thing? 9/7 divided by the previous one is 3/7, which is 9/7 times the reciprocal, 7/3. 7s cancel, I get 9/3. And indeed, 9/3 is 3, and so yes, okay, we're good to go. And so if I give you a sequence on a quiz and say, is it geometric, is it arithmetic, or is it neither, you might want to check more than one, because if I gave you this, 1, 2, 4, and you just check one of them, yeah, okay, 2, 1 is 2, 4, 2, okay, and then that looks like a geometric sequence, okay. It couldn't be arithmetic, because the difference here is 1, the difference here is 2, so you say, oh no, that's not arithmetic. But I might give you something like this, 1, 2, 4, 6. And you go, okay, well, the difference here is 2, the difference here is 2, wait, oh, no, sorry, the difference here is 1, the difference here is 2, the difference here is 2. So it can't be arithmetic. Is it geometric? Well, 2 divided by 1 is 2. 4 divided by 2 is 2. Ooh. 6 divided by 4, oh, 6 divided by 4 is, well, 6 divided by 4. I guess, what, 3/2. So it can't be geometric, can't be arithmetic, so we conclude it's neither geometric nor arithmetic. Okay, so, but anyway, okay, the whole point was they told you this is a geometric sequence. Find the common ratio. And it's nice to just check more than one place, because maybe you did your math wrong on one of them, right? So, okay, so that's that. On number 4, they tell you to find the nth term, find the 5th term, and find the 8th term of a geometric sequence. And in number 4, this is the sequence that they give us. So in order to do any of this, like just looking up here, right, in order that you want to find, in fact, if you find the nth term, like then you could easily get this, because if you know a formula for the nth term, if you want the 5th, you plug in a 5 right there, and you'll have a1 times r to the 4th. You want the 8th term, you know that would be a1 times r to the 7th, and so forth, right? So really, this comes down, and all we're going to do here is just find the nth term. Okay? In order to do that, we need to know what r is. So I'm going to take the next one, divide by the previous one. And so I have 1.2 divided by 4. Now, we could break out long division, or I could multiply the top and the bottom by 10, giving me 12/40ths, which is the same as 6/20ths, which is the same as 3/10ths. And I personally, this is the way I'm going to use it. I mean, they gave you decimals, right? So maybe you want to answer it in decimals. Maybe you want to do this. Right, I think 3 divided by 10 is 0.3, last time I checked. So that if you want to go down that route for this one, since they gave you decimals, okay. But I'm telling you, especially later on today, when you see what we're going to do, fractions are going to be easier, be much easier on you. So if you want to do it in fractions, that's cool too. But okay, so we have R, but let's just check and make sure, right? They told us it's a geometric sequence. Let's just make sure we got the right thing. I think it's 3/10. So let's take that one divided by that one and make sure it's the same thing. So I'm going to go 0.36 divided by 1.2. And it should give me 3/10. So, okay, how about, there's a bunch of ways I could do this. The easiest one is I multiply top and bottom by 100, and I have 120 right there, right? So that's the same thing as 6 times 6 over, I'm going to do this the dumb way. How about 12 times 10? 6 times 6, and how about, what's that? There's a 3 in there. 3 times 4, and that's a 2 times 5. Okay, so let's see. Oh, why not? 2 times 3 times 2 times 3. Now I'm certain I won't be messing this up. Okay, 3's cancel, 2's cancel. I have another 2 in here, so that's a 4. So that's a 2 times 2. Cancel out a 2, and now I have a 3 over 2 times 5 is 10. Yes, indeed, 3/10. Okay, good to go. Now, what you could do, because you do have to find the 5th term, you have the 4th term right here, you could just take this and multiply it by that to get the 5th term, if you want. Then you get the 8th term by just, you keep doing that to get to the 8th. But I think it's a bit more slick to go ahead and say, well, all right, let's just find the nth term. A sub n is a1 times whatever r is, which we know is 3/10, raised to the n minus 1. A1, in this case, is 4. So we have 4 times 3/10 to the n minus 1. Now, that's my claim right there. Let's check it. Because when I plug in, this is my A1, this is my A2. When I plug in A2 into here, I should get 1.2. Or 1240 is however it works out to be, right? So let's just see. A2 is supposed to be for 3 over 10. Plug in a 2. 2 minus 1 is 1. So that's the same thing as 4 times 3 over 10. That's 12/10, which is A2, 12/10. There we go. Yes, 12/10 is 1.2. So yes, I got the right formula. I feel good about that. We could do that again to check that one and so on and so forth. But we found the nth term. So that means you could get the 5th term and the 8th term very easily by plugging in a 5, plugging in an 8. You're good to go. Number 12. Same prompt. Find the nth term, 5th term, 8th term of this geometric sequence. Oh boy, there's a variable in there. Oh, what do? Don't think about it. It's this exact same thing, okay? Since it's a geometric sequence, you could find r by taking this and divide it by that. That was really easy, right? Negative x over 3 divided by 1 is just negative x over 3. It's that simple. That's all r is. Let's check it just to make sure, okay? Please do check your stuff, because it should be the same thing if I take that and divide by that. It should give me the same r. If I go x squared over 9, divide by negative x over 3. Okay, so that is, you take the numerator, and then you multiply by the reciprocal of the denominator. Okay, yep. 1x cancels with the x on the top, and I get an x. The 3 cancels a 3 on the bottom, giving me a 3, and it's a negative times a positive, so I have a negative. Now we could find the nth term by just plugging this stuff in, right? We say, okay, an is going to be a1, which is just 1, okay? I could write it as 1 times, and then I take the ratio, which is negative. Now, parentheses are going to be really important here because you don't want to mess that up. Negative x over 3 or negative x thirds, whatever. Boom, right there. Okay? That 1 is just bugging me. I can't do it. I can't do that. Okay, there we go. So there you go. That should be it. Let's check, okay? Plug in a 2. Since this is a1, here's a 2. Clearly, if I plug in a 2, I get 2 minus 1 is 1, and it's just that. So that makes me feel good. Let's check the next one. Let's check that A3 does give me that. A3 gives me negative x over 3. Now, 3 minus 1 is 2. So negative thing squared is positive. X squared is x squared. And on the bottom, we have 3 squared is 9. Yes. Let's do one more. Let's check the fourth. The fourth is negative x over 3. 4 minus 1 gives me 3, so I go to the third. Now, a negative cubed is negative, so it gives me negative x cubed on the top. 3 times 3 times 3 is 27. As we expect, okay? So you could find the fifth by just doing this one more time, raising that to the fourth instead. Should be a positive. Should have x to the fourth on the top, whatever that times 3 is on the bottom. And again, right, all we're doing is each time, you'll notice each one of these is just the previous one multiplied by this number right there. Take that, multiplied by this, you get that. Take this, multiplied by this, you get that. So then to get the next one, you take this, multiply by this to get that, or use your formula. It's all the same thing, right? Eighth term also gonna work. Yeah, so that's it for that type of problem. Number 20, given a geometric sequence with the second term, a2 is equal to 3, and the fifth term, a5 is equal to negative 81, tells us to find r and find a9, the ninth term. Pause it and try it. So there's a bunch of different ways we could go about doing this. I like, but the way I'm going to do it is I know that if I could find out what the nth term is, if I could get a general formula for the nth term, that's going to make my life easier. So in order to do that, now you'll notice this is what I'm about to do is very similar to what we would do if we had an exponential function and you were given 2 points here. So if you remember, right, like let's say you plug in a 2 and you get something, you plug in a 3 and you get something else, right? Here's some number y1, here's another number y2, and you know that this thing, f of x, is some kind of e to the k x. And the way we went about dealing with this, if we wanted to find that number and that number, right? Those are the 2 bits we're trying to find. In order to find 2 unknowns, we need 2 equations, right? And so you would plug in your 2 and set that equal to whatever the output is. You plug in your 3, set that what equals whatever the output is. Let's get some actual concrete numbers. Let's say this is, I don't know, how about 6? And we'll say that this is 12. Okay? The way that we would do this is we say, well, let's just get 2 equations. The way we do that is we plug in a 2, get out a 6. So you'll plug in your 2, get out a 6. But what does that mean? That means that 6 is the output whenever to the 2 is the input. And you say, okay, plug in your 3, you get out a 12. So that means e to the k 3 right there. And then it's like, well, now what do you do, right? It's not like a nice linear equation where you just plug one into the other or subtract them from each other or add them to each other. What we wanted to do here was divide them by each other, if you remember. A couple ways we could do that. One way is this. There we go. 6c e to the k times 2. And what happens, that's nice, that gives you a nice 2. Those guys cancel. And then this we could rewrite as e to the k3 minus k2. Or how about just e to the k? And then you take the log of both sides and you get that k is equal to natural log of 2. And then you go back in and blah, 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 blah. Well, let's just think for a second. Look at this. That's exponential, isn't it? Like what I just wrote here, like f of x was some constant times e to some other constant times x or whatever like that. You'll notice this is very, very similar here. So in the same way that an arithmetic sequence we talked about for a second, it's always going to fall on a line. Right? Because you're going up. Every time you go over one, you go up by the exact same amount each and every time. Well, now with a geometric sequence, every time you move over by one, you're multiplying by something else. That sounds much more like this. So you have some number. Let's say it's 3. Then you go over one unit. Sorry, I'm not going to shift it. You think you see what I'm saying, right? Now you go over and like our original case, it was 3, 6, 12, 24. Each time you go over by one, you're multiplying by a constant, right? And so you multiply by 6. Then to get the next one, when you go over one more, you multiply by 2. Here you go over one more, you multiply by 2 to get up to 24 and so forth, so on and so forth. This that we're doing is very similar to 3 times 2 to the k minus 1. It would be plus 1, whatever. Oh, sorry, x, if we're doing this, if that's my x-axis. So what I'm getting at is that whereas a arithmetic sequence, the points all fall on a line, with a geometric sequence, this r right here plays the role of your base. And it should be, you know, the plus and the minus, we're shifting, and I get that. And remember how I said some start you off at 0. Sometimes sequences start off where the subscript is at 0. That would make this a lot nicer. But then it's kind of a pain because you have to say, well, wait a minute, if you're on the nth term, that's actually n plus 1 things that you have, so there's a trade-off there. But the idea is if each time you move over one, you're multiplying by another constant amount, what you're getting here is it's like an exponential function. And just whatever the r is the base. So our original one was like 3 times 2 to some power, right? So our original function was something like this, right? The function corresponding to our original sequence was something like this. And so now we're given 2 data points, right? When the input is 2, the output is 3. When the input is 5, the output is that. And since this thing is very similar to, or you could even think about it as a special case of an exponential function, we're going to use the same method we would use if you're given 2 points on an exponential function to find the actual formula for the function. And so, that's a long-winded way of saying so since A2, we could think about A2, that's the same thing as A1 times R, right? I'm just using that formula right there. That's how did you get A2? Well, you took the original thing and you multiplied by the common ratio. How did you get A5? Well, you took the original thing and you multiply by the common ratio a total of 4 times, right? Straight up using that right there. That's all that is. But now we have outputs. So when the input was 2, the exponent was 1. That's kind of weird, but you know, the output is that. Now when the input is 5, exponent is 4, but the output is negative 81. And now we're going to use these two equations in the same way we would have with exponential functions to get at this. So I like to take the bigger one and put them on top. I'm going to say a1 r to the 4th is equal to negative 81. Now I'm going to divide by that guy. a1 r and 3. A1's cancel. Very similar to the exponential functions, huh? Interesting. We have 4 on top, 1 on the bottom. That leaves you a 3 right there. Negative divided by a positive is a negative. And now, 81 divided by 3, you could check me on this. I believe it's 27. That sounds right. So now, something to note. I could take the cube root of both sides, and I get one and only one answer. Actually, you get 3 answers if you're talking about complex numbers. We're only talking about real numbers right now, so you get only one answer here if I take the cube root of both sides. If I were taking a square root, it would be different, wouldn't it? Yeah, it would. And you'd need to think about that. Okay? If you're taking a square root, or a 4th root, or a 6th root, any even root, you would get more than one possibility. That might be helpful in your homework. Now, okay, so we took the cube root of r cubed, it's just r. Cube root of a negative just stays negative. That's perfectly fine, and it should be 3 right there. Okay? So, where are we? It told us to find r. Nice. Now it told us to find a9. Okay, one thing I could do is, since I know r and I know 5, I could say, well, since I know a5 is negative 81, then a6 is what I get when I take a5 and multiply by r. And a7 is what I get when I take that previous thing and multiply by another r. And then so on and so forth, so that a9 would be a5, whatever that is, times r to the 4th. That's cool. And if you want to do it that way, that's great. I think it will be to your benefit to do this instead, to practice this. So, practice what? I didn't say. To practice getting the general formula. Now we have r, the only thing we're missing is a1. But in the same way that you would solve that you would find a function, an exponential function given 2 points, right? Once you know one of the unknowns, which you do here, you could take that and plug that back in to either of these to find your other unknown, which is a1. Because remember, that's the goal here. If I could get a1 and if I could get r, then I know everything I need to know about this sequence. And so, we have r. That's nice. Let's go ahead and get that. Let's get the an down. We have an is equal to a1 times, now r, it tells me is negative 3, so I go negative 3 times n minus 1. Now the only thing I need that I have left over is the a1. And since I have r, I could get it right here. Could also get it right here. Life will be a little bit harder if you do it that way, but if you do it right there, life is easy. And so I'm going to say a1 times r, which we know is negative 3, is equal to 3. So I just took this and plugged them into here. And lo and behold, I get the a1 is equal to negative 1. And so now I have my general formula, which I could just write as, I'm going to write it like that, negative 1 times negative 3 to the n minus 1. Right there. Notice I use the parentheses, because you might, if you see something like this, negative something raised to a power, you might think that that applies to that, which it only would if you were doing this right there, right? So I'm just trying to be a little bit careful, and I'm saying, whatever I get from doing that exponentiation, like I plug in a 5 and it tells me -3 to the 4th, so it comes out to be positive. Then I multiply by a negative, so it makes it negative, so on and so forth. And from there, you could find your 9, just plug in your 9, or you could get your 9 this way, however you want to do it, that's cool. I do suggest you get familiar with that, because they easily could have just said, instead of find R and that, they could have just said find AN, the nth term of the sequence, and boom. In fact, like on a quiz, I can imagine that you might have a teacher who on a quiz would tell you this instead of what your homework problem was telling you to do. I said earlier that I was going to not use R after a certain time. I was going to use something else. And I'm sorry for this, but I think with what we're about to do, you'll see why I want to do this. But we could have used any letter, right? Like you have some ratio, I could choose any letter, and given any general sequence, it's unknown what the ratio is going to be. And so usually when we think of unknowns in math, we think, well, if you have an unknown number, we usually call it x. And then instead of r to the n minus 1, we'd have x to the n minus 1. Now suppose that we have some geometric sequence right here. Okay. Well then another way of writing this thing with this right here, like we discussed, right? A1, how do you get to the next one? Well, you multiply by whatever this is. So this would be A1 times x. To get to the next one, you just multiply by x again, giving you A1 times x or x squared. And then A1 x to the third. Then you have an A1 x to the fourth, and so on and so forth. Now, and notice, now I'm bringing in the second to last one here. And so, if you remember, we'll do it this way. The last one was 1 away, so x to the n minus 1. In fact, the formula is right there. So then the previous one would be A1 x to the n minus 2. Just down one more, right? So you take x to the n minus 1, n minus 2, n minus 3, n minus, all the way until you get down to 4, 3, 2, 1, 0. X to the 0th is just 1, so that's nice. Okay, so this is another way of writing any geometric sequence. You give me any geometric sequence in the world, and it's going to have this form right here. That's exactly what it's going to be. It's just that the only question is what's A1 and what's x. Okay? Now let's say that I want to find the nth partial sum of this. So in other words, what I want here is I want to take each one of these n terms, and let's just make sure there are n of them, right? Because if that's 1, 2, 3, 4, all the way up to n minus 1, there's n minus 1 of them, and then you're adding on one more, so you have a total of n of them, okay? And we want to add them up, so instead of having commas here, we're just saying, let's plus them all together, okay? So we're going to plus these together. That's all a sum is. We're saying plus all these guys together, okay? The first thing to notice is that there is a constant term in every single one of these, or there's a constant number in every single one of these, and it's A1. So that means we could factor it out, right? Well, let's do that. Because we want to try to wrap our minds around this. Maybe there's an easier way of writing it. I don't know. Maybe there is, right? And so what happens when I factor out that from there? Well, I'm left with a 1. Then I'm left with an x. Here I'm left with an x squared. And so on and so forth, all the way up to x to the n minus 2, x to the n minus 1. A total of n terms right here, right? So then that's the question. The question is, can I rewrite this thing in a way that makes it easier to compute? Well, one thing that would be really easy is if x happened to be 1. Okay, so let's just go ahead and take care of this one case here. If x is indeed equal to 1, well, first thing to notice is that the sequence would be constant, wouldn't it? Because if each time you're just multiplying by 1 to get to the next one, well then this would just be a constant sequence. And if you're adding up all the terms of a constant sequence, it would just be, well, whatever the first thing is times the number of things that you have. Or you could look at it this way, is that if each one of these x's were 1s, you'd have 1 plus 1 plus 1 plus all the way down to 1. And you'd have how many 1s? Well, n of them. There would be n of them, and you'd have a1 times n. Right? We saw that last time. There's nothing new here. So that would be, well, it would be a pretty silly case. Would you even call it geometric? You wouldn't even call the sequence geometric if it's just a constant sequence. Technically it is, because you could write it this way, but it's a really boring sequence, right? And this would reduce down to a1 times 1 to the n minus 1, which would just be a1. So every single one of them would just be whatever the first one is. Very boring. And so I guess technically it's a geometric sequence, but if that's the case, you wouldn't be talking about this in the first place, right? If the ratio were 1. So let's suppose that x is not equal to 1. Okay, that's what we're going to do. We're going to say, okay, in the case where x is equal to 1, it's so easy, and you could just add up however many. You just take however many things you're adding together and multiply it by the first term. N times a is 1. So when x is not equal to 1, what can we do to this thing? So what I'm trying to do right now is wrap my mind around this. I want to know, what is this thing? Is there another way I could write this thing that might be simpler? Indeed there is. And there's a trick. This is a trick. Like, I never would have thought of this. Like if you gave me this problem before I knew this trick, you said, is there a simpler way of writing this? Boy, I don't know. And you could work on it and try to find a bunch of different things. You probably factor some stuff and group some stuff, and it just gets more and more complicated. And then once you see this trick, you go, ooh, huh, that's what you could do. Here's the trick. You take this thing that you're working on, and you multiply by 1 minus x. Now, let's do that. You've taken this is a polynomial, right? You take your polynomial and you're multiplying it by a binomial. And so you could think about this as distributing this into each one of these. The way I like to do it is I take the first bit and distribute it into each one of these. So I take 1 times 1 and it gives me a 1. 1 times x, and it gives me an x. 1 times x squared, it gives me an x squared. And I keep doing that all the way up, and I get my x to the n minus 2, plus 1 times x to the n minus 1. Now I do it with the other one. I take negative x, multiply him through. I'm going to distribute him into each one of these. Negative x times 1 gives me negative x. Notice I've offset this a little bit, so that I could go ahead and group the like terms better. X comes into here and gives negative x times positive x gives me a negative x squared. Negative x times negative gives me a negative x third, and so on and so forth. Now, I haven't written it, but there's an x to the n minus 3 right there. Terrible. And so then when negative x comes in and hits him, he comes out to negative x n minus 2. Okay. Then the negative x comes in and hits this x to the n minus 2. And it brings his power up by 1. And it's negative because of that negative. And so we get x to the negative n minus 1. And finally, we do this last multiplication. He comes over. Negative times a positive is a negative. X to the n minus 1. Adding on one more power gives me x to the n. Now I take all of these and add them together, and I get 1. Well, plus minus cancel. Plus x squared minus x squared cancel. And all of these guys cancel until I get to here. Those cancel. That one and that one cancel out, and what I'm left with is minus x to the n. And so, this times this is the same thing as 1 minus x to the n. Now, let's just verify that, because that's a little bit abstract. We're using a bunch of n's and n minus 2 and n minus 3 and all that kind of stuff. Let's just do a concrete example. 1 plus x squared. Now, the formula tells me that if I take this 1 minus x and multiply it by that, I should get 1 minus x to the 1 more power, right? Whatever the last thing here is, it should be 1 power higher, okay? So if that's a 2, then this should be 3. Is that what we get? Well, let's just do it. The 1 distributes over, I get 1 plus x squared. Now the minus gives me minus x and 1 gives me minus x. Minus x and x gives me minus x squared. Minus x and x squared gives me minus x cubed. 1, 0, 0, minus x cubed. Yep, 1 minus x cubed. Okay? Okay. Now, how does that help me? Like, that's not, this isn't what I was looking for, you know, but this is what I was looking for. This is the thing that I'm trying to wrap my head around. Because I said, is there a way of simplifying this? Maybe. Maybe there is. It looks like there is. Because what did I say? If x is equal to 1, this is trivial. In fact, you wouldn't even call it a geometric sequence to begin with. I mean, you could, but yeah. Now, if x is not equal to 1, then 1 minus x is not equal to 0. The only way that that thing's equal to 0 is if x is equal to positive 1. So if x, this next step that I'm going to take, if x is not equal to 1, that's the only restriction we have now. As long as x is not equal to 1, then I could divide both sides by this. That cancels, and so this entire thing right here is the same thing as 1 minus x to the n over 1 minus x. So I'm going to write that right here. Minus x to the n over 1 minus x. I don't know about you, but I have a hard time believing that. Like, that just seems, it seems you've wrapped that up in a nice little package here. I'm going to go ahead and put over here on what? This is assuming x is not equal to 1. Okay. Okay. So, wait a second. Let's just check this. Okay. Oh, look what I didn't do. I'm sorry. That's that part. That's that part right there. We're missing that guy. I haven't written him yet. Okay. So, what's in the parentheses is equal to that, like we just showed, and then that a1 is on the outside there. There you go. Okay. Now let's just verify this for something. Let's say that x is equal to 2. And I want to do this. 2, how about 4, how about 8? Okay, so 1 plus 2 plus 4 plus 8. That's 10 and 5, that should be 15. You'll notice why I chose those, right? That's 1 plus 2 squared plus 2 cubed. Yeah? Let's just make sure. 1, yes. 2, yes. 2 squared is 4. 2 cubed is 8. That sum should be 15. But this tells me, right, remember, that the sum as we go up to x to the n minus 1 is the same thing as 1 minus x to the n, the next power up, 1 minus x. So in this case, my x is equal to 2, and my power here, the n minus 1, is 3, so this should be the same thing. My formula tells me it should be the same thing as 1 minus x, which in this case is 2, raised to the next power up, which is 4, over 1 minus x, which is 2. So let's just check it. 1 minus, so 2 to the 4th is 16. 1 minus 2 is negative 1. 1 minus 16 is negative 15. Negative 1. Ho! Ho! It works. That's interesting. Let's do one more, because it doesn't just work. As long as x is not equal to 1, this should work. So let's do something like this. How about 1 plus a half plus a quarter? Now what is that? That's, how about 4/4 plus 2/4 plus 1/4. So that's some number of quarters, and it's 4, 5, 6, 7. 7 quarters. Okay? What you'll notice at this, we could rewrite this as 1 plus 1/2 plus 1/2 squared. So we're in this type of regime right here, right? Where it's like you have some value that's coming up by a power every time, and you're adding them all together. Okay? And so this should be the same thing as 1 minus whatever that thing is. 1 minus whatever that thing is. And then since that's a 2, this needs to be 1 power higher. Should be 3. What goes in there? Well, it's a 1/2. So that's a 1/2. Okay, so let's just compute that. 1 minus 1/2 cubed is the same thing as 1/2 times a half times a half, or 1 over 2 cubed, which is 1/8. So that's 1 minus an eighth. 1 minus a half is just a half. Right? So I'm just going to say on the bottom we have a half. Okay. So that's 8/8 minus 1/8. That should be 7/8 on the top. Divide by 1/2. Yeah, let's check myself here. That should be 7/8. 1 minus half is a half. Yes, okay. Divide by fractions, multiply by the reciprocal. So that's the same as 7/8 times 2 over 1, which is 7 over 4, which is what we got the other way. Cool. There's one more I want to do. Check this out. So forget all of this that I wrote here to begin with. And let's say that I presented you with this. Now, looking at that, you might say, well, wait, there's a minus in there. Minuses don't, there's no minuses in here, so the formula is not going to work. You're right. If there's minuses in there, the formula is not going to work. So we have to rewrite it so that there's no minuses in there. And what we could do, and this is, we talked about this, you could think about it as an alternating series, right? Positive, negative, positive. And if we continued it on, if it went negative, positive, then this tells you that, well, maybe there's a -1 somewhere. And you could absorb that -1 into here. And is this the same thing as that? Yeah, right? 1 plus a -1/2 is the same thing as 1 minus a half. And then plus a -1/2 squared, well, when you square it, it comes out to be positive, so that works. Okay? And so let's just see what happens. How does this change? Well, the only thing that changes is that this should now be a negative right here, and that should be a negative right there. That's going to change everything. There we get. But, oh, sorry, let's actually compute this, right? So this was 4/4 minus 2/4 plus 1/4, which is the same as 4 minus 2 is 2 plus 1 is 3, so that should be 3/4 right there. That's that bad boy. Okay, now let's do this. On the bottom we have 1 minus minus. So 1 minus a negative is the same thing as plus a positive. That's the same thing as 2 halves plus a half, so that's 3 halves on the bottom. Now on the top, we have 1 minus. Now you have a negative number cubed, and so it stays negative. So it should be -1/8, but minus -1/8 is the same thing as plus a positive 1/8. And so we have 8/8 plus 1/8. That should be a total of 9/8 on the top. Does everybody buy that? I think so. I think that works, right? Cube a negative, it stays negative. Cube the 2, it becomes 8. 1 minus that thing is 1 plus that thing. That's 8/8 plus 1/8 is 9/8. Yes, okay, good. So now let's keep going. That's the same thing as 9/8 times reciprocal gives me 2/3. The 2 cancels, leaves me a 4. The 3 cancels, leaves me a 3. And so I have 3/4. Is that what we got? Yes. Indeed, it works. So, like I said, the only thing that we have to assume is that x is not equal to 1. And if x is not equal to 1, it could be negative. The x could be a negative number, right? I don't think we talked about, oh no, we had one where the ratio turned out to be negative, and we saw that the series alternated. Or I'm sorry, series, I keep saying that. We'll get to series. That the sequence alternated, right? We saw that in the previous, it was the one that was given where A2 was 3 and A5 was negative 81. And what we found was that R was equal to negative 3, right? And so that can happen. This is, if your R is a negative number, that's perfectly fine. It could be bigger than 1. It could be smaller than 1. As long as it's not 1, this formula always works. So for a geometric sequence, AN, we have the partial sum, the nth partial sum of this guy is just the sum of the first n terms, right? That's all this means. And you might think, okay, well then we have a formula for that. That's A1, whatever the first one is, and then 1 minus x to the n, 1 minus x, where x is the ratio, which is where you take any of the next terms and divide by the previous term. You might think this is a good way of keeping that in your head. I suggest that you do not think about it this way, that you have this formula. Rather, so I'm going to say, don't, like, this is true, but I'm going to say don't think about it that way. What I'd rather you keep in your mind is this: 1 plus x squared all the way up to x to the n minus 1 is equal to 1 minus x to the n over 1 minus x. This will be much more useful for you in the future. And it'll prevent a possible problem that you could have right now with this type of question. Because if you have this in your head and you're trying to figure this question out, you might just say, oh, okay, well, the r, or the x, is negative 1/5. You're going up to 9. And so it looks like the A1 is just a 1. And so you go 1 minus this. Going up to 9, so you go 1 more. Or no, I'm sorry, you go up to 9. Sorry, yes, that is the case. N and N, they match up. And 1 minus and all that, blah, 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 blah. 1, not so much. 2, it's much better to think about this. So what I suggest you do, and I do this to this day, anytime I do a sum, the first thing I do is write out some of the terms. Okay? So I'm just going to write this out. It starts off with k equals 1. When k equals 1, we have negative root 5. Okay? Then we add that to. When k equals 2, we have negative root 5 squared. And so on until we get to the last one, which is negative root 5 to the 9th. Now you'll notice this is not in this form right here. Right? What this is, if you think about it, this is x plus x squared plus all the way up to x to the 9th. That is not the same thing as that right there. Right? Although, we'll see in a second. I think it's much better to say, well, hold up. I know this is the thing that I know. And so I'm going to pull out an x. If I factor out an x, now I'm in. Now I can just directly apply this right here and say, 1, because it's starting at 1 and going up to 8. So that means then I need to bring it up to 9. Okay? And so I'm going to say x times 1 minus x to the 9 over 1 minus x. That's the type of thing I want to do. So that's what I'm going to do right here. That's how I suggest you go about doing this. Because it's very easy, and they're going to be tricky with these. They're going to try to trick you up with these. And so in order to do that, don't think about it as a formula. Think about this fact, and then try to apply this fact here. So when I'm looking at this, I'm going to say, well, I don't have a 1 plus stuff. So that means I need to factor something out. I'm going to factor out that first one right here, negative root 5. What's left? Well, 1 plus negative root 5 plus, and then so on and so forth, all the way up to the last one, which is negative root 5. But now instead of being to the 9th, it's to the 8th. Right there. Yeah? Okay, so what is that? Well, negative root 5 times, well, this is that, and so we raise the power up by 1 more, and we go 1 minus the thing to the 9th, 1 minus the thing. What is that thing? Negative root 5. Okay, negative root 5. Now, I mean, we're technically done, but let's kind of simplify this a little bit. We could write this as negative root 5 times 1. So that's an odd power, so it will still be a minus. So a minus minus would be a plus. And then I could write that as root 5 to the 9th. Yeah. And then 1 minus minus is 1 plus root 5. I'm not really worried about getting any more fine-grained than that. Like, we could have just left it right there and we would have got the same thing, right? Now, it turns out that if you had just plugged it in this case, I think you would have ended up with the same thing, right? If you just say, well, A1, well, actually no, because if you're looking at that, you'd say, well, what's A1? Well, I guess it's just 1. If you're looking at that, you'd say it's just 1, and you'd be wrong because you'd be missing that guy right there. You see, and this is what I'm getting at here is when it comes to sums and stuff like that, like trying to plug stuff into a formula only works if the formula is exactly the way that you expect it to be. But with sums, there's so much variability. For instance, here's another for instance of why you want to write up a sum. So this is a perfectly good answer, or this one's a perfectly good answer for that right there. But just to illustrate my point of why you want to write this stuff out is, let's say that instead of the sum going from 1 to 9, they gave you the sum as k goes from 0 to 9. How's that going to change? Well, let's write it out, right? Because obviously, that even if you tried to just plug it into this formula, it's not going to work, because here you're going from 0, here you're going from 1, so you can't say that n is equal to 9, and then if you try to, I mean, it's just a pain. Always just write out your sums, okay? So when k is equal to 0, you have something to the 0th power, which is 1. Then you add that to k equals 1, and so it goes to the first power, and so what's this? Let's do another one, plus what? Well, the thing that now when k equals 2, blah, 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 and it goes all the way up to root 5 9th, okay? And now we are in this place here, where we have, it's the sum starts with 1, and its ascending powers, just like a polynomial, right? 1 plus x squared, that's your 1 plus x squared, and so on, all the way up to x to the 9th. And so now, this is in that form, so I could just say that's the same thing as 1 minus x to the, instead of 9th, it's going to be 1 more power, so to the 10th. 1 minus x, and so the x is negative root 5. Negative root 5. And so I guess you could simplify this if you want. A negative to an even power is positive. And so we could just write it like that. Negative is a positive 1 plus root 5. It's good enough. This one's also good enough, right? You're good to go right there. My point is, don't think about it this way. Try to write out your sum and rearrange it or manipulate it and so that you have some part of it that fits this right there, and then use that fact to move forward. Number 24, again, find the sum, same thing. Here's another reason why you don't want to just memorize that formula. You want to try to rearrange this so that it does this thing to give you this, okay? Because the first thing you might notice, like I told you, like write the sum out, okay? So we do that, and if you just blindly do that without really thinking about what you're trying to do, you're going to get this. You're going to say, okay, when k equals 1, you have 3 to the negative 1, plus k equals 2, you have 3 to the negative 2, plus, and so on all the way up to the negative 7. And you say, wait a minute, that looks nothing like this. Wait, what? And so, knowing that this is a very useful trick whenever you have sums, like, my initial thought is like, I'm not even thinking about this, I'm looking at that and saying, well, wait a sec, can I rewrite this so that it's some number to some power that's going to increase 1, 2, 3, 4, and so on? And, you know, there's a few different ways you can see this. You can say 3 to the negative k is the same thing as 1 over 3 to the k. Still doesn't help you. But if you realize that that's the same thing as 1/3 to the k, now your life is much easier. And so, I mean, maybe you start off writing it like this, and maybe you then rewrite it as 1 over 3 plus 1 over 3 squared plus all of that, and then 1 over 3 to the 7. And you're like, that still doesn't look like this until you realize, oh yeah. This is the same thing as 1/3 plus 1/3 squared plus all of that. And 1/3 to the 7th. Right? Now you're in a place where you could start manipulating this to turn it into that. Or you could have, from the very beginning, knowing that this is the game that you're going to play, and this is how I probably would have done it. So, again, right, if this is the natural way that you go about to get to there, cool. I think about it more like this. I say, well, wait a second. That's the same thing as 1 over 3 to the k, but that's not going to help me. I want some number raised to the k, so I rewrite that as some number raised to the k. I cannot tell you how useful it is that when you see a sum, you stop and ask yourself, can I rewrite that so that it's one number raised to the index? So, like for instance, if I have j equals 1 and up to some number n, and I have some kind of thing, maybe it's something similar like this, maybe it's like 1, 2 to the negative j, I'm going to ask myself, can I rewrite that so that it's one number? Can I rewrite this so that it's the same thing, so that it's one number raised to the j power? And in order to do that, I would say, well, 1 over 2 to a negative power is the same thing as flip the sign and make it to the positive power, so then I could rewrite that as that's what I want, 2 to the j. And that will make your life easier. Why? Because if you could do that, then you get it into this form right here, and we have this nifty thing. And this is going to be a game that you're going to play for a long time in math, is that when you have a sum, one of the first questions you should ask yourself is, can I take what's in here and rewrite it so that it's one number raised to this power right there? So if you can, you get this, and everybody's happy, okay? So that's my first step. I ask myself, can I take that, raise it to one number raised to the k? Yes, I can. Now let's write that guy out. So I'm going to write that out. When k equals 1, we get 1 over 3. Add that 2. When k equals 2, we get 1/3 squared. Add that 2. Keep going until you get all the way up to when k equals 7, you get that. Now I'm going to say, well, wait a second. That's not quite that thing yet. I need a 1 in the front. So I need to factor out a third. That's what I'm going to do. I'm going to take 1/3 and factor it out. And when I do that, what's left over? Well, the third factors out as 1. That third factors out, leaving me a third. And so on, all the way up to 1/3. Now instead of to the 7th, it's to the 6th. And yes, I am in this form here. I have 1 plus something plus, and that something is getting raised to a higher power until we get up to here. Therefore, That's the same thing. Don't forget this. It's so easy to forget this. Remember when I first wrote this out, I forgot the A1 that I had factored out. And when I first derived this little thing, I forgot the A1 that was sticking out in front of it. Yeah, it's real easy to forget this. So there's that. Now, 1/3. So we're going to have 1 minus a third. 1 minus a third, like that. But now, instead of to the 6th power, we go up one more to the 7th power. So that's the same thing as a third. 1 minus, how about 1 over 3 to the 7? 1 minus a third is what, 2/3? I mean, it'd be cool if you could simplify this as much as possible. So this is 1/3 times 1 minus 1 over 3 to the 7th times the reciprocal, which is 3/2. That's all multiplied by each other. You see what I did there? I just took the denominator, it was in the denominator, brought it up into the numerator, and then I just kept him over there. The 3's cancel, and I guess I get 1 minus 1 over 3/7 all over 2. That looks nice. We could probably go on further from there. In fact, you can multiply the top and the bottom by 3/7, and you get, I'm sorry, 3/7. 3 to the 7. 2 times 3 to the 7. That's another one. Although, whatever, right? Really, like, I won't mind if you leave it like this. But when it's something really simple that you could do right here, 1 minus a third, go ahead and minus the third. And then, like, if you notice, come on, there's 3's. Those things are going to cancel. Make it look a little nicer. But whatever, that's not really the point. The point is that you could take something weird like this and rearrange it so that it turns into something like this, so you could apply this fact. Here's the last one we're going to do. This is find the sum. And now you'll notice, even if you wanted to use a formula, there's no way you're going to be able to. Okay? And also, here's something else to notice. This is the thing that you're summing up, right? This is going to be this, something like this plus something else as you're changing k. And we have a j in here. That j does not change when k changes. So as far as this sum is concerned, this thing is just constant. Whatever j happens to be, maybe we found out like 5 pages ago that j was 6. Okay, well now he comes in. He's not changing as k changes. It's something to notice, okay? Another thing to notice is, if you remember, you have a sum of anything with the ai's plus bi's. Okay, yeah, we use k's, but whatever. We said that's the same thing as the sum of the ai's plus the sum of the bi's. This might be a great place where you use that. It might make your life easier, as opposed to, well, I'm going to plug in a k into here, and then I'm going to plug in another, and blah, 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 until, yeah, and then, like, and if you wrote that out like this, so when it's 8, it's 3 to the 1 plus 2 to the j squared. And then you go, okay, now it's 3 to the 2 plus 2 to the j squared. Now this thing is messing up your life, right? So what I suggest is you go ahead and just rewrite it as 2 separate sums. So I'm going to say this is the same thing as k goes from 8 up to 14 of the first one, k minus 7. And then I'm going to take that and add that to this sum, which is over the same numbers, k equals 8 to 14 of 2j squared. Now, like I said before, this is a constant with respect to k. This is not going to change. Whatever j happens to be, he ain't changing when you change k. When k is 8, j is j. When k is 9, j is still j, right? So that is just that's a constant, right? Now we're in this realm, right? You have a constant as n goes from, or let's say k goes from 1 to n. We know that's just n times the constant. But now we're not going from 1 to n, we're going from m to n. And so if you remember, it's the big one minus the small one, and then you add 1 because you've forgotten about the first one when you do the subtraction. If you don't remember, check out the last. If you don't remember that, check out the last thing. So, in other words, it's just the number of things that we have, right? This bit right here, I'm going to go ahead and do and say that's the same thing as 14 minus 8 plus 1 times the constant, which is 2j squared. Okay, 14 minus 8, 8, 9, 10, 11, 12, 13, 14 is 6, plus 1 is 7. So it should be 7 times 2j squared. That would be 14j squared, is what that is right there, right? Now, let's just make sure we have 8, 9, 10, 11, 12, 13, 14. Yes, you should have 7 of those. Just going back to the very beginning, remember what I was writing was 3 to the 1 plus 2j squared plus 3 to the 2 plus 2j squared. All that is by the time you get to the last one, which is whatever it would be, 3 to the whatever plus 2j squared, the total number of them that you should have, if you were to count them all up, should be 7. That's all that is. So you have 2j squared plus 2j squared plus 2j squared 7 times. You would have 7 times 2j squared. That's how I got that right there. So this part of the sum, but instead of putting it in here, I spread it out or split them apart, did that sum to give me that. Okay, so that's going to come back later. Now I just need to figure out that other part here. So I'm going to go ahead and do this right here and say, well, when k is equal to 8, 3, 8 minus 7 is 1. So we have a 3 plus. K is equal to 9, we have k, 9 minus, that's 2, 2. All the way up to the last one is when k is equal to 14, then minus 7 should give you a 3 to the 7, just like that. So that's that part of the sum right there. The other part is this part right here, which we already knew was 14 j squared. We are not quite at this yet because we need to get a 1 in the front. So I'm going to factor out a 1, or I'm going to factor out a 3 to give me a 1 in the front. And so here we go. 3 times 1 plus 3 squared all the way up to 3 to the 6th. Okay. Now I can apply this right here. And I'm going to get rid of this stuff over here. You saw how we got it. And I'm going to say, okay, it's the same thing as 3. Do not lose your 3. And don't lose your other stuff either. Okay, I'm copying all this down. So that is like that. And so we have a 1 minus. What is the base? It's a 3. Or the x in this case is a 3. And so it's 3 raised to the, instead of 6, we go up 1 more to give me a 7. And then down here we do this. So 1 minus 3 is negative 2. So that's 3, negative 2 on the bottom. 1 minus 3 to the 7th plus 14j squared. We're technically done. I hate having a negative there. So I'm going to say, well, throw the negative up there. And that should be a perfectly good answer right there. This is a perfectly good answer right here. That's fine too. That's fine. They're all fine, right? You can do any one of those. But I mean, if you want to clean it up, if you want to be nice to your teacher, do something like that. And you might wonder, I'm glad that this happened, because you might say, well, wait. I can factor out a negative 1 from each one of these if I wanted to. X to the n, 1 minus x. I mean, that's the same thing as negative 1 times negative 1 plus x to the n. Negative 1 plus x. The negative 1's cancel, and then I can rewrite that as x to the n minus 1, x minus 1. Why didn't you do it that way? And indeed, like when I first wrote out the sum, I could have done it that way. I could have said x to the n minus 1 plus x to the n minus 2 all the way down to x2 x is 1. And then I could have taken that and multiplied it by x minus 1. And we would have found that, yeah, indeed, it's x to the n minus 1. And then you divide that over here to give you that right there. And yeah, that could work. And you could think about it that way if you like. What we're about to do next time, you're going to see it will be slightly more convenient, just barely more convenient to keep it like this. When you lock that into your head, which I want you to do. I want you to lock this into your brain. Please lock this into your brain, okay, for the rest of your life. I cannot tell you how often this thing comes up, and it's like so often in my life, I've been faced with something like this, and then I go, oh, right, boom, and then life gets really easy. And so I really, really suggest that you do it, and that you think about it this way and not this way. Again, this is true. You could think about it like this. It'll make your life just a little slightly easier if you do remember it this way. There's rhyme to the reason. So you got homework. Please let me know if you have any problems with it. Get up with me as soon as you can, and I will see you next week.